I'm very pleased to introduce the speaker today, is Professor Paul Rosenbaum from University of Pennsylvania. So for those of you who are in causal inference, who are familiar with causal inference, you will have heard about Paul's work on propensity score. But he also has many other very, very interesting work that I always feel is not appreciated enough by the community. His work on sensitivity analysis, but also on the evidence factors. And he has this really nice crossword puzzle as an analogy of what we're doing with observational studies that personally, I had a tremendous impact on how I think about causal inference. Paul couldn't be here today, unfortunately, but he very kindly agreed to give us a talk online on his recent work. And I really like your title, Paul, is being realistic about unmeasured biases in observational studies. I think we all need to be aware of that, be realistic about that. So just one quick word before we start. So we'll have Paul speaking for about 50 to 55 minutes. And we'll save the questions till the end. At the end, I'm going to start with questions from the live audience. Then maybe we take a couple of them from online as well. So without further ado, Paul can take the stage.
Great. Thanks for that kind introduction. I'm going to talk about being realistic about unmeasured biases in observational studies, and I hope what I mean by that emerges as we go along. An observational study is a study of treatment effects when we can't run a randomized experiment. Treatment received and outcome exhibited may be associated in an observational study in the absence of any effect actually caused by the treatment. Although we always adjust for measured covariates in an observational study, it's possible the groups still differ in terms of covariates that were not measured. A better way of saying that is that without randomized treatment assignment, the probability of treatment may depend on relevant covariates that were not observed. This is the main source of controversy in an observational study, and consequently it organizes the design and analysis of an observational study, so this source of controversy can be addressed. The talk has some theory, some methods, and an example. In thinking about unmeasured bias, context matters. The talk is going to use a simple example, almost a toy example, in which the context is familiar to everyone since we kind of live here. I'm going to make some quick claims about how observational studies should be designed if we want them to be insensitive to larger unmeasured biases. Proofs of these claims are in my design book, and I'm not going to spend a great deal of time on them. I'm going to spend more time talking about how the choice of statistical methods has a substantial effect on the degree to which a study is sensitive to unmeasured biases. Perhaps surprisingly, even when we find evidence that there's unmeasured bias, that evidence may make the study insensitive to larger unmeasured biases. The example has several control groups, so I'm going to say a sentence or two about the role of the several control groups. The example and a lot of what I'll be talking about is in my 2025 book. The data are in the associated R package, ITOS. I have a few general theses that I'd like to persuade you of. The first is that every observational study is affected by unmeasured biases, but that fact is not debilitating. The studies of smoking and lung cancer were affected by unmeasured biases, but we have complete confidence that smoking causes lung cancer. Unmeasured bias is unmeasured, but it often has detectable consequences. These detectable consequences may heighten or may diminish our concern that the ostensible causal effects are spurious. A sensitivity analysis talks about unmeasured biases, but it is computed from, it's a function of the observable data. So its stochastic properties are functions of the observable distributions, that is, the distributions of observable data. Change the observable distributions by changing the study design. Change the observable distributions by changing the analysis, and you change the sensitivity to unmeasured biases. We didn't have guidance from statistical theory about the previous point. It would be easy to make poor decisions in design and analysis reporting that your study is sensitive to very small biases when that's just a consequence of mistaken choices of study design or methods of analysis, not a feature of the world. The toy example involves HDL cholesterol and light daily alcohol consumption. So HDL cholesterol is the good cholesterol. You want higher levels of it. You often hear or read that a glass of wine each day with dinner prolongs life, reducing cardiovascular mortality, perhaps by increasing HDL cholesterol level. A recent position paper by the American Society of Clinical Oncology, the big clinical oncology group, is sharply critical of this claim, emphasizing an increased risk of death from cancer, as well as increased risks of death from accidents, liver diseases, and violence. Purely as a methodological example, just to show statistical methods in action, we're going to look at a small corner of this problem, alas, not the most important corner, namely whether light daily alcohol consumption increases HDL cholesterol. For some discussion of a more central question of whether mortality is reduced by light daily alcohol consumption, I would point to my paper in 2025 in Chance. So in our toy example, we're looking at adults age 20 or more from the NHANES survey from 2013 through 2016. At this time, NHANES and the Centers for Disease Control described binge drinking as drinking 4 or 5 drinks in a day. If you did that fairly quickly, you would be more or less legally drunk by the usual definition, although those are different concepts. The treated group here doesn't binge drink, or at least typically. The treated group drinks between 1 and 3 alcoholic drinks on most days, meaning on 260 days in the last year, with a median of 520 drinks in the last year. That's group D for daily drinkers. There are 3 control groups. Control group N for never had fewer than 12 drinks in their life and a median of 0 in the last year. Control group R for rarely had more than 12 drinks in their life, but fewer than 12 drinks in the past year, and they never had a period in their lives when they engaged in binge drinking on most days. And they too had a median of 0 drinks in the last year. Control group B, former binge drinkers, had a period in their lives when they engaged in binge drinking on most days, but stopped and currently drink, if at all, on at most 1 day a week. And they had a median of 4 drinks in the last year. So I want you to take a moment and think about people in these groups. You probably know people in each of these groups, people who drink a little bit every day, people who never drank in their life, people who raise a glass at a wedding or a wake, but otherwise have no interest in alcohol, and people who are had problems with binge drinking or excessive drinking in the past and have stopped through some means or other and are still dealing with some issues, perhaps, or not. I want you to think about those people. Probably you know some of them, and think about what else is going on in their lives. What else is going on in their lives is the unmeasured biases in an observational study. We have an observational study which has 406 blocks of size 4, 1 person from each of our 4 groups, matched for age, sex, and education. So this is showing you a little bit about what they're like. They're actually matched for another thing as well. So NHANES, to save money, doesn't record every test for every person. And so they randomly take a sample and measure additional things. In particular, there are some people who had methylmercury levels measured. So the matching paired people based on whether they were in the subsample with methylmercury or without the subsample, just a random subsample. There are 200 blocks where everybody had a methylmercury level, 206 blocks where nobody had a methylmercury level. You notice that the daily drinkers were, before matching, mostly men. 2/3 were men. The never drinkers and the rare drinkers were mostly women. 2/3 were women. The former binge drinkers were again mostly men. The matching has corrected that. Everybody's 34% female. The daily drinkers were a tad older on average than the 3 control groups. That also was corrected by matching. The daily drinkers had a little bit more education. They had on average some college, meaning about 2 years of college. whereas the typical member of the control groups had more like a high school degree. What's this stuff with multiple control groups? Why do we have multiple control groups? Campbell and Bitterman had the clever idea that if you haven't measured a variable, you could still perhaps find two control groups in which that variable is very, very different. And if you could show that despite the big difference in this unobserved variable, the outcomes were pretty similar, then that unobserved covariate ceases to be a very plausible explanation of why the control groups differ from the treated group. So that's the idea of control by systematic variation. You'll notice that the study, as it's been designed, is omitting people who drink milk toast levels of alcohol, say they have 2 drinks a week. Omitting diluted versions of the treatment increases insensitivity to unmeasured biases. So you can easily prove that, and it's done in the book. Blocks of size 4, 1 treated, 3 controls, are better than matched pairs. They're better at distinguishing a treatment effect without bias from a bias without a treatment effect. Why is that? Well, in matched pairs, what would happen if the treatment increased the response? You would see pairs, and the treated person would tend to have a higher response than the control. What would happen if the treated and control responses came from the same distribution in each block, and somebody's pushing the higher order statistics into the treated group, a selection bias with no treatment effect? Well, you'd see the same pattern. The treated person would tend to have the higher response. It's a little different with 1, 2, 3 match sets, right? Because if I have 1 treated person, the treatment is hitting that 1 person and not the 3 controls. In contrast, if I'm looking at 4 observations from the same distribution and somebody's pushing the larger order statistics into the treated group, that has a slightly different appearance. You can think about a very extreme example where the treatment effect is enormous. You'd have 1 guy through the roof and 3 guys who are order statistics from the same distribution versus 4 order statistics from the same distribution, and those would look somewhat different. In practice, if you looked at a single block, you couldn't see this, but if the pattern is a little different, we can design statistics so they're sensitive to this difference and gain a little bit in terms of how insensitive to bias statistics are. There's an unaffected outcome, methylmercury. We talked about it a little bit. The World Health Organization and CDC say that almost all human exposure to methylmercury comes from eating fish and shellfish. People have looked for methylmercury in alcoholic beverages and haven't found it. So we don't think that alcohol is causing people to have high methylmercury levels. We think it's from eating fish or shellfish. Can we use this in some way? So this is a picture of the data. So on the first picture, you're seeing DN, RB, daily, never, rare, former binge drinkers, their age, then their education. So they look pretty comparable in age and education, and they're all 33.7% female. And finally, you have the HDL cholesterol levels in the groups. And you notice that the daily drinkers have somewhat higher HDL cholesterol levels than the 3 control groups, which look similar. So if you go through a fairly standard calculation comparing the 6 groups pairwise and adjusting for multiple testing, you find that the daily group is higher than the 3 control groups with a p-value of 10 to the minus 16th, and the control groups don't differ from each other with a p-value greater than 0.21. And so whatever we're looking at in the right picture, it isn't chance. Chance is off the picture. It might be biased treatment assignment, it might be an effect of alcohol, or it might be a combination of the 2 or something else, but it's certainly not an accident. So do you think these people are living similar lives? My first thesis was that there are always unmeasured biases in observational studies. So here we're looking at some other NHANES questions. Have you ever tried marijuana or hashish? Daily drinkers, 73% of them said yes. Never drinkers said 9% of them said yes. Rare drinkers, 25% of them said yes. Former binge drinkers, 75% of them said yes. Have you ever tried cocaine, heroin, meth? 29% of the daily drinkers said yes. 4% of the never drinkers said yes. 37% of the former binge drinkers said yes. In terms of methylmercury in your blood, it's higher for daily drinkers, even though we don't really expect that to be a consequence of drinking and think that's something about their diet. Have you been to the dentist in the past year? 67% of the daily drinkers said yes. 48% of the former binge drinkers said yes. All these differences are wildly significant and are not, again, not due to chance. You notice that the systematic variation notion of Bitterman and Campbell is happening, right? The never drinkers, 9% have tried hashish or marijuana. The former binge drinkers, 75% have. Even if we hadn't measured that, we would have systematically varied it by using 3 control groups. How important is it that somebody who tried marijuana maybe once? Probably not very important, but the difference is striking, 73% versus 9% in one of the control groups. Tell me there's somebody in this room who's surprised by this, right? I mean, you knew this was going to happen as soon as you thought about comparing people who drink daily to various other groups. They're going to differ in all sorts of ways, and we have to deal with it. Here we're going back to the 200 blocks where we have methylmercury levels. So on the left, you're looking at just the HDL cholesterol levels for the people who also have methylmercury levels. And on the right, you're looking at the methylmercury levels for the people who have methylmercury levels instead of the 406 blocks. What do you see? Well, on the left, you see something we're not sure quite what we're looking at. Could be an effect of alcohol, could be a bias in who drinks. On the right, we're pretty convinced that methylmercury comes from eating fish. And it's not a consequence of drinking alcohol. So on the right, we're seeing what seems to be some sort of bias producing a difference in the 2 groups. And the curious thing would be the 2 pictures look a lot alike, right? And so can we go off and interpret the left picture as a causal effect if we're pretty convinced that the right picture is not a causal effect? And we'll come back to that. So I'm going to give a little structure for this. I imagine a lot of this is familiar, so I'm going to go through it fairly quickly. The slides are a little more detailed than what I'm going to say, so if it's not familiar, read the slides to pick up the notation. Treatment is either you're a daily drinker or not. That's indicated by Z. Causal effects are potential outcomes depending on whether you are a daily drinker or a control. We only see one of your 2 potential outcomes, the outcome under the treatment you actually received, that's cap R. Outcomes may be multivariate, for example, cholesterol and methylmercury. We also have observed covariates X, and we're worried about unobserved covariates U. In a randomized experiment, what do? Maybe we block people using some function of the observed covariates, and then we flip a coin to decide who's the treated person in each block. Do that independently in distinct blocks. The coin is fair in the sense that the coin coming up heads doesn't depend on the potential outcomes, or more precisely, treatment assignment is ignorable given the observed covariates in a randomized experiment, which is given by expression 1. That says what? It says these probabilities are never 0 or 1, there's some randomness, and also the probability of treatment given the observed covariates and the potential outcomes is equal to the probability of treatment given just the observed covariates. They're conditionally independent. If treatment assignment is ignorable, then causal inference is comparatively straightforward. It's just a problem of ordinary estimation, right? But condition 1 is problematic in essentially every observational study. We often speak of ignorable given something else. So we might say, I don't want to really adjust for all of X. I just want to adjust for a function of X. Is it ignorable just given the function of X? Or I might say, well, it would have been ignorable if I'd only measured one unobserved covariate, but it's not ignorable without the unobserved covariate, which is focusing our attention on a particular unobserved covariate and consequences of not measuring it. So the term is often used in slightly varied forms. The guys in expression 1 have names. So, for example, the probability of treatment given the observed covariate is the propensity score. And it's a familiar fact that if treatment assignment is ignorable given X, it's ignorable given a scalar, namely given the scalar propensity score. The second guy is also a familiar guy. He's the principal unobserved covariate. He conditions on the 2 potential outcomes in addition to X. He's unobserved because we never see the 2 potential outcomes together, so we never see the principal unobserved covariate, nor can we estimate it. If the principal unobserved covariate is never 0 or 1, then 2 facts follow. The first is treatment assignment being ignorable is the same as the propensity score equaling the principal unobserved covariate. That's not a theorem, that's just expression 1 in English. Secondly, treatment assignment is always ignorable given any function of X and the principal unobserved covariate. So if we had the principal unobserved covariate, treatment assignment would be ignorable and it wouldn't be otherwise. and consequently, the principal unobserved covariate is the whole ball of wax so far as unobserved covariates are, and really the whole ball of wax so far as causal inference is concerned. Importantly, he's a function of the potential outcomes and the observed covariates. So we build a block with design with I blocks and J people per block, 406 blocks with 4 people per block and 1 treated person in each block. We did that by sampling data from the observable distributions and assembling them into blocks. Perhaps we blocked using some function of the observed covariate, so it's the same for people in the same block. Our worry is that blocking hasn't controlled the principal unobserved covariate. That could happen in any of 3 ways. It could be that controlling for h of x didn't control for the propensity score. It could be that controlling for h of x didn't control for the principal unobserved covariate because treatment assignment is not ignorable given the observed covariates. Or it could be that both are true, right? It could be we did a lousy job of adjusting for the observed covariates, and on top of that, there are unobserved covariates. Let's write calligraphic F for the potential outcomes and observed covariates for the people in our study. The principal unobserved covariate is a function of calligraphic F. Let's write calligraphic Z for the set of possible treatment assignments. So what's a treatment assignment? A treatment assignment is an I by J matrix, 406 rows, 4 columns. It's binary coordinates, and it has 1 and 3 zeros in every one of the rows. So the set calligraphic Z contains J to the I possible treatment assignments for our study. We sample people and block them so that the treatment assignment is actually in calligraphic Z, and I'm going to abbreviate that as conditioning on the treatment assignment being in calligraphic Z. And I'm going to further abbreviate that as just conditioning on Z, which isn't quite right, but it makes things look a little prettier. So for example, in a randomized block design, what we really mean is that the probability of treatment in each block is 1 over J for every person, 1/4 for every person. I want to move from the principal unobserved covariate to what is left of the principal unobserved covariate, having blocked for the things I blocked for. So to do that, I need to condition on the fact that I have 1 treated person in each block. So we'll do that in 2 steps. What's the chance that person IJ is treated and the other people are controls? That's given by this expression. And then I take that expression and sum over all the people who might be the treated person to get condition on the fact that there's 1 treated person in each block. And that gives me a new guy. He's theta IJ. He's what's left of the principal unobserved covariate, having adjusted for the blocks. So the thetas add to 1 for each block, right? Their probabilities within each block. The sensitivity analysis in terms of the principal unobserved covariate is going to work with what's left of the principal unobserved covariate that we didn't deal with by blocking. There are 2 ways of expressing it. We can go back to the population before we blocked, and we can talk about the behavior of the principal unobserved covariate. And the sensitivity analysis says for 2 people who might be blocked because they have the same value of h of x, the relative odds of being the treated person are between gamma and 1 over gamma. Gamma times more likely than I to be the treated person because of the difference in the principal unobserved covariate. Or if you do a second's worth of algebra, you realize that in terms of the residue of the principal unobserved covariate within the blocks, where the probabilities sum to 1, that's the same as the ratio of 2 of those probabilities being between gamma and 1 over gamma. So we're done with the structure. I want to go back to the central parts of the talk. I said that different statistics and different research designs correctly yield different levels of sensitivity to unmeasured biases. So we want to understand this so we can make wise choices in the design and analysis of observational studies. So we're first going to do that in the alcohol data, and we'll see something happen, and it will happen in a fairly dramatic way. A natural question would be, is this something that happened in one data set and will never happen again, or is it a law of nature? So we're going to replace the alcohol data where we don't actually know what's going on by a probability model, which we created, and therefore we do know what's going on, and we'll discover that it's a law of nature. It happens always with probability models of a variety of familiar forms. We're going to start by looking at a closely related collection of statistics. It's important that they are closely related because only one thing's going to vary in this collection of statistics. And when that thing varies, very dramatic things are going to happen. So we'll know exactly why these statistics are different from each other. We're testing the null hypothesis of no treatment effect. We're going to do this with weighted rank statistics. So we're going to rank within each block from 1 to 4 the responses of the 4 people in the block, calling the ranks Qij. We're also going to look at the ranges of the 4 responses in a block. There are 4 responses. We're going to rank the ranges from 1 to I and divide by I, so we get a rank score that's between 0 and 1. We're then going to score those ranges using a function phi. And it's the choice of the function phi that's going to vary across these statistics. The test statistic says the block I is worth phi of W, its range, and we're going to multiply that by the rank of the treated person in block I, and we're going to sum that over all blocks. For pairs, taking phi to be 1, ignoring the ranges, gives you the sign test. Taking phi equal to the identity function that returns whatever is given to it yields Wilcoxon's signed rank test. And for general phi, you're getting a general signed rank test, which has been studied for decades. For j greater than 2, for blocks bigger than pairs, taking phi equal 1 yields the blocked Wilcoxon rank sum statistic. That is the other rank Wilcoxon statistic. We're looking at the rank in each block. We get the rank of the treated person in each block. We add that over all the blocks. That's summing up a lot of Wilcoxon rank sum statistics. It's probably the most commonly used rank test for block data. It's in Layman's nonparametrics book. If I instead use phi of W equal to W, then that gives us the signed rank statistic for pairs, but for blocks it gives us Quade's statistic, which was proposed in 1979. These are the proposed phi functions. So the phi function, remember, is weighting the ranges in the blocks. The horizontal line is giving you the blocked Wilcoxon rank sum statistic or the sign test for pairs. The diagonal line is giving you Wilcoxon's signed rank statistic for pairs or Quade statistics for blocks. And the 2 Cobra-like guys are the new guys you may not have seen before. So they're called U because they're derived from a U statistic. Notice what they do. They ignore blocks with small ranges and increase the weight up to a certain point and then level off as the ranges get bigger and bigger. And we'll see they actually behave very differently. Very important set is B gamma. B gamma is a set of possible biases. That is a set of possible bias treatment assignments, theta, a set of possible residues of the principal unobserved covariance. What is B gamma? B gamma is the set of all thetas that are compatible with a particular value of the sensitivity parameter gamma. So in order for that to be the case, the thetas have to sum to 1 in each block, and they have to have a ratio of at most gamma or at least 1 over gamma in every block. So we can look at all possible thetas that do that. In our data set, we have 406 blocks of size 4. Each theta, therefore, is of dimension 1624, but all of them live in a flat of dimension 1218 because they sum to 1 in every block. B is a closed and bounded set, and hence a compact set of theta matrices. That's relevant to optimization. The sets are nested. A bigger gamma means the set gets bigger. It includes everything that was in the previous set and even more. So as gamma gets bigger and bigger, we're assuming less and less about theta. Every theta which is not deterministic, every theta which never has theta equal to 0 or 1, is in B gamma for some large enough gamma. So if you gave me a treatment assignment probabilities which are not deterministic, I could find you a gamma which would include that matrix theta. So in that sense, we're not assuming anything about theta except that it's not deterministic. We're simply drawing marks on a yardstick for how far this theta is from randomized treatment assignment. A randomized block design has theta equal to theta bar, where theta bar is just 1 over j for every person, right? Which is the same thing as saying that the true residue of the principal unobserved covariate is in B1. B1's a set which just has one matrix in it. The central problem in an observational study is there's no reason to believe that theta is in B1. And as soon as gamma is bigger than 1, the problem is not identified. There's no consistent estimate of treatment effects at that point. We're going to test the null hypothesis of no treatment effect. We're using our test statistic, the weighted rank statistic we talked about. We know the probability that a particular treatment assignment arises. It's kind of a multinomial-like probability involving the principal unobserved covariate. And our problem is we don't know the principal unobserved covariate. Let's write bracket A for the indicator function of an event. So we're going to reject the null hypothesis if the test statistic is bigger than some number little t. What's the probability that we falsely reject a true null hypothesis? It's going to be this quantity, right? So it's an indicator which is picking out the cases where we reject, and the probability of those treatment assignments, and we're summing that over all possible treatment assignments. Our problem is we don't know theta, so we're going to take the largest p-value that is in B gamma, right? So we maximize that p-value over all theta in B gamma. And that's the bound, an upper bound on the p-value. It's a realized upper bound. There is a theta in B gamma that produces that p-value. So let's do that in our example. So this is, again, testing the hypothesis of no effect of daily alcohol on HDL cholesterol. We have 4 test statistics. They differ by what weight they attach to the ranges of the blocks, and we have various values of gamma. So if we assume there's no unmeasured confounding, crazy assumption in an observational study, but if we assume that, all the p-values would be extremely tiny, and it wouldn't matter which statistic we used. If gamma were 2, fairly big bias, but not enormous, still all of the p-values, the maximum p-value you can get from a bias of gamma equal to 2 is still negligible. At gamma equal to 3.5, Wilcoxon statistic, the analog of the sign statistic, is petering out, and some of the p-values are above 0.05. The maximum p-value is 0.06. But the other 3 statistics are going strong. At gamma equal to 4.5, much bigger than 3.5, Quade's statistic is still rejecting the null hypothesis, but it's about to give up. But U868 and U878 are still going strong. At 5.5, U868 has just barely given up and is producing some p-values above 0.05. But U878 is still going strong. At gamma equal to 6, U878 is still rejecting the null hypothesis, but it's about to give up. To put this in context, smoking and lung cancer would easily be sensitive to gamma equal to 6 in Hammond's 1964 prospective study of smoking and lung cancer. So HDL cholesterol and like daily alcohol consumption is more insensitive to bias than one of the most solid conclusions we've ever reached on the basis of observational studies. But only if you use the right test statistic, and only if you design the study in the right way. If you used, for example, Wilcoxon statistic, it would be much more sensitive than smoking and lung cancer. And if you hadn't done a block design and you hadn't done left out the intermediate doses, it would be much more sensitive than it is here. All of them have those features. Is 1 to 3 really better than 1 to 1? I kept saying that it was, so I want to support that conclusion. Do a fair comparison. It's not fair to compare 406 1 to 3 blocks to 406 1 to 1 pairs. There's twice as much data in the blocks. So we have to reduce the number of blocks in some ways to make an equitable comparison. Just for that purpose, I'm going to think about a Gaussian linear model with additive block effects, a constant variance, the model we all learned in kindergarten. So the estimator is going to be the treated minus control difference in means in our block design. If I have M 1 to 1 pairs, I would have, that estimator would have variance 2 sigma squared over M. If I have I 1 to 3 blocks, that estimator would have variance 1 plus 1/3 sigma squared over I. So I equate those two guys, and I find that 406 pairs is worth 271 blocks. in what sense is it worth it? Well, they have the same expectation, they have the same variance, the estimators. They both be Gaussian distributed estimators. So I wouldn't be able to tell the distributions apart. That seems like a fairly equitable comparison so far as this simple model goes. So let's do that with the data set. On the left, I took my 406 blocks and I sampled one control from every block, so I got 406 pairs. On the right, I took 271 of the 406 blocks at random and threw away the rest of them. On the left, what are you seeing? This is the same sensitivity analysis we were looking at before, but now with pairs, right? Disaster has struck, right? Everything is much more sensitive to unmeasured bias than it was before. The p-value for Wilcoxon's statistic at gamma equal to 3.5, it just barely exceeded 0.05 in the previous thing with block design. Now it's 0.99. U878, which had been insensitive to gamma equal to 6, is now sensitive at gamma equal to 4.5. In contrast, if we go to the right side, where we have 271 1 to 3 blocks, the situation is a little different than it was before. You'd expect that. You'll throw away about a third of the data. Notice that U878 is now sensitive at 5.5 or so rather than 6, but it hasn't changed very much. It's more like what you would have expected had you just lost a portion of your data. So pairs are much worse than the block design so far as sensitivity to unmeasured bias is concerned. Can we understand this theoretically? Is this just something that happened in the alcohol data and we don't know why, or is it really true all the time? So we're going to let the sample size go to infinity. When we let the sample size go to infinity, our statistic is going to get a subscript reflecting the sample size at the moment. We're still going to have a block design. The block design has causal effects that are symmetrically distributed about tau. I'm going to standardize tau in the following way. I'm going to take as the atom of this study one treated minus control pair difference. So I take a treated person, I take a control, I take their difference, and I look at that. Tau is going to be in units of the standard deviation of that. So if I looked at one treated minus control pair difference, that guy is going to have expectation tau, and tau is in units of the standard deviation of that guy. We'll start off with tau equal 1/2 and then vary it a bit. We're also going to imagine that the study is unaffected by unmeasured biases, namely the treatment assignment is ignorable. This is the case where we want to say the results are insensitive. After all, there is a treatment effect and there's no bias, and we're really looking at a causal effect. We don't know it because we don't know whether the treatment assignment is ignorable, and we don't know whether there's a treatment effect. But this is the thing we want to distinguish from bias with no treatment effect. So that's what I just said. This is called a favorable situation. So the favorable situation has a treatment effect and no bias. The unfavorable situation has bias and no treatment effect. Can we tell them apart using different designs and study and statistical methods? So the null hypothesis says there's no treatment effect, but there's a bias of magnitude less than or equal to gamma. And the alternative hypothesis is given by that favorable model, right? Can we tell them apart? So let's fix a gamma. We'll vary gamma eventually, but let's fix a gamma. Say gamma equal to 2. We have I blocks, maybe 406 blocks, and we want to know, we want to study with power 0.9, let's say. Then there's a level of the test, alpha sub gamma I, that achieves that power. It may be a crazy level, a reasonable level. Like 0.01 would be a reasonable level, 0.05 would be okay. If I had to take alpha equal to 1 to get 90% power, that means the only way I could reject with 90% power is to ignore the data and always reject the null hypothesis. And that wouldn't be a wise thing to do, right? So alpha is an index which is telling us about how well we can get 90% power. It's better than other ways of thinking about it because it works with non-identified situations. When the situation is not identified, the level I need for 90% power is going to go to something ridiculous, like just always reject the null hypothesis, don't care about the data. And that's telling you that you've hit the lack of identification. For gamma equal to 1 in you get the level of a randomization test out of this. And as I say, you may need very high levels of gamma. At very high levels of gamma, alpha may be near 1. What we're hoping to see is what? That the level is going to zero as the sample size goes to infinity, and we'd like it to go to zero as fast as possible. At the level of resolution of this calculation, the actual power doesn't matter. So if you change it from 90% power, you get the same answer for 80% power or 50% power or 95% power. There's typically a number called the design sensitivity, such that if you do the sensitivity analysis with gamma set below the design sensitivity, this level is going to zero, as it would in conventional statistical analyses. That's our normal world. If you do the sensitivity analysis with gamma bigger than the design sensitivity, then the level is going to 1, telling you the situation is no longer identified. You can't tell this null hypothesis from this alternative. And all that happens is the sample size gets bigger as you become ever more certain that you can't tell. So gamma tilde, the design sensitivity, is a feature of the favorable model, not a feature of a data set. And it's telling you the limiting sensitivity to bias as the sample size goes to infinity from that particular model. If gamma is below gamma tilde, so the level is going to zero, we want the alpha to go to zero as fast as possible, right? And there's typically a Bahadur slope which characterizes how fast it's going to zero. Alpha is typically tending to zero at an exponential rate, and the rate is going to depend on the favorable model and whether you picked a good study design and good statistical methods. The ratio of two Bahadur slopes is the Bahadur asymptotic relative efficiency, so that has many of the same interpretations as Pitman efficiency, but Pitman efficiency doesn't work with non-identified models, because what Pitman efficiency does is it lets the treatment effect get very small, but if the treatment effect is very small, then the study is very sensitive to very small biases. You're not learning what you really wanted to learn. What you really wanted to know is if the treatment effect is big enough to care about, and the bias is big enough to worry about, can I tell them apart, right? You're not really interested in infinitesimally small treatment effects, which are sensitive to infinitesimally small biases. Here we're looking at some design sensitivities. Again, this is no longer about the data. This is about the normal distribution. The normal distribution where the treated minus controlled pair difference has an expectation that is half its standard deviation. And what are you seeing? We're seeing this for pairs and for blocks of size 4, for Wilcoxon statistic, Quaid statistics, and the 2U statistics. And what you're seeing here is essentially what you saw in the data set, right? The design sensitivities, which are properties of the model now, not properties of the data, are better for blocks than for pairs, and they're better for U878 than they are for Wilcoxon statistic, and they look comparable to what we were looking at before. If you change tau and make it smaller, say to a third, you get a similar pattern, but smaller values of gamma tilde. So I've quoted some of those values here. If you change the error distribution from a normal distribution to a T5 distribution, a T distribution, central T on 5 degrees of freedom, the pattern, the values are actually almost identical to what you're seeing for the normal distribution. Here we're looking at Bahadur asymptotic relative efficiency. So I'm computing it at gamma equal to 2. You can compute it at anything you want. And we're going to look first in the upper portion of this table at a reasonable statistic, U868, compared to itself for pairs. So how good is it to have blocks rather than pairs if I use a reasonable statistic? The asymptotic relative efficiency, therefore, is 1 in the first row because I'm comparing the statistic to itself. I have two possible treatment effects, a third or a half, and I have either the normal distribution or the T distribution on 5 degrees of freedom. And what are you seeing? You're seeing that, in fact, blocks bigger than pairs are a big aid in terms of efficiency. So an efficiency of 3 means that a relative efficiency of 300% increase in efficiency. 3 observations done wrong are worth 1 observation done right. Why am I doing gamma equal to 2? Well, in this comparison, the values in this table, the design sensitivity is always bigger than 2. So all of these guys have Bahadur efficiencies in the conventional sense. If we had passed the design sensitivity, some of these would be infinity and some of these would be 0, depending on whether the better statistic would be infinitely better than the worse statistic. The bottom portion of the table is the double whammy. You pick the wrong statistic, you do the wrong study design. What's the wrong study design? Probably match pairs, and you used the traditional statistic, Wilcoxon signed rank statistic, Quaid statistic in blocks of size 2. That would be the comparator, and we're looking at doing U868 in varying sized blocks compared to the conventional thing, Wilcoxon signed rank statistic for matched pairs. Here you're seeing values that range over quite a large range, including a value of 24.81 on its way off to infinity as the design sensitivity is passed. So this is saying that there's a 2,481% increase in efficiency from using the better design with the better method. In statistics, we usually get excited about 10% increase in efficiency, 15% increase in efficiency, but this is a 2,481% increase in efficiency. We ought to care about something of this sort. I want to go back to the data on methylmercury. So remember, we're now looking just at the 200 blocks with methylmercury levels recorded. And on the left, we're looking at our outcome, HDL cholesterol, and on the right, we're looking at methylmercury, and we thought that that was probably a sign that the daily drinkers were eating more fish, because we don't think that alcohol causes methylmercury. This is actually formally a test of the null hypothesis that theta is equal to theta bar. On the right, we know there's no treatment effect, and so we can't explain that difference as a treatment effect. We have to explain it in terms of some way theta differed from theta bar, and when we do an ordinary test, say Quaid's test, we get a p-value on the right that is too small for R to calculate. So the hypothesis that there's no unmeasured confounded has been completely rejected by the methylmercury data. So what should we make of that? We've just rejected that B1, that theta's in B1, right? That theta is equal to theta bar. To avoid lots of different calculations, I'm going to do all the tests using Quaid's test, the test for bias, the test for treatment effect. It turns out that's not actually smart. Quaid's test is a good test when you're testing for bias. It's not so great for testing for effect. And so you could find out more about that in that statistical science article, but I don't want to get distracted by that. I'm just going to use a reasonable test for everything, Quaid's test. Using the 200 blocks, rejection of the null hypothesis of no treatment effect on HDL cholesterol with Quaid's test becomes sensitive at gamma equal to 3.614. If I made gamma a little bit bigger, I would get a p-value above 0.05. No theta in B 3.614 leads to a p-value above 0.05, but some are close. In parallel, if I do that with the methylmercury data, I find that no theta in B 1.993 is plausible because all of those are rejected with a p-value less than 0.05. So that's telling you not only that there's unmeasured confounding, but there's a lot of it, right? The smallest gamma that can explain what we saw in the methylmercury levels is about gamma equal to 2, which would explain much of, typical studies you read in the journals. So there's a lot of bias in this comparison, and that's pretty strongly demonstrated by the methylmercury levels. Nonetheless, the sensitivity analysis does not require amendment. The sensitivity analysis said nothing in B 3.614 could explain the effect on HDL cholesterol. And all of B 1.993 is inside B 3.614. So nothing that we're forced to believe by methylmercury is actually an adequate explanation. It has to be bigger than that. And the sensitivity analysis stands as it was before. It hasn't been changed by the test for bias. That's not a given. It happened in this example. Part of B 3.614 is particularly troublesome. Why is it troublesome? Because there are thetas in B 3.614 such that they are on the exact boundary. They give you a p-value of exactly 0.05, and if I made it 3.615 as gamma instead of 3.614, the p-value would jump above 0.05. So those are the troublesome boundary points. Most of B 3.614 isn't like that, but there are a couple of spots where theta is about to cross to above 0.05. We would like to say no theta in the troublesome points, the ones which are about to become sensitive to bias, is actually plausible. We can use that same cholesterol data to test the points in the troublesome set. If we could reject those points, we could say, well, it's true the sensitivity analysis says the results are sensitive to 3.614, but the points at which that's true are not plausible because the methylmercury data has rejected them. In which case we say there's no gap between the test for bias and the sensitivity analysis. When the sensitivity analysis, which knows nothing, is giving up, this test for bias is saying, I know something, and what I know is relevant to the sensitivity analysis. So when we do test the troublesome points in the methylmercury data, all of the troublesome points are rejected with p-values less than 10 to the minus 7th. So although the sensitivity analysis is worried about those points, they're not remotely plausible in the data set. So in this case, there's no gap. And in fact, the sensitivity analysis is being strengthened by the test for bias, which is rejecting the points of maximum sensitivity. We could carry this further. We could take all of the thetas and test them all. Test every possible theta and keep the ones that are not rejected in a set cap theta. So that's going to be from first principles a confidence set. So if we test it at the 0.05 level, we would get a 95% confidence set for theta. It's a funny set because it's not consistent. It's not, as the sample size goes to infinity, we're not going to get to know what theta is, but we've seen that we can reject some thetas as clearly wrong, even though we can't get a consistent estimate. Why can't we get a consistent estimate? Because the dimension of the guy is getting bigger as the sample size gets bigger. There's no hope of getting a consistent estimate of theta. We can have an informed test for bias. The informed test for bias says, I'm not interested in thetas that the methylmercury data have rejected. I only want to look at the thetas which are plausible in light of the methylmercury data. I don't want to look at those troublesome points. Those troublesome points aren't plausible. They have a p-value of 10 to the minus 7th. They're not right at all. So I'm going to confine theta to b gamma intersect the confidence set. So that's a smaller set, right? So this is, the top guy is the p-value, the sensitivity analysis informed by the test for bias. The bottom guy is the sensitivity analysis without that information. These are the upper bounds on the p-values over those two sets of thetas. If I maximize over a smaller set, I get a smaller maximum. So p prime, the informed p-value, is always less than or equal to p gamma. The information is never harmful, it could be beneficial. In the HDL cholesterol level, P 3.614 is 0.05, uninformed at 3.614 gamma, but P prime at gamma equal to 3.82 is also 0.05. So it's a bigger bias that is needed to explain both parts of our analysis. For those of you who know what an amplification is, this is saying that the difference between 3.614 and 3.82 is nothing to sneeze at. Let me summarize what we've been saying about the HDL cholesterol and methylmercury data. The smallest bias that can explain the left-hand side is 3.614. The smallest bias that can explain the right side is 2. But the smallest bias that can explain both sides, it's harder to explain both sides, is 3.82. So the test for bias has actually made the results less sensitive to bias because it has to explain both pictures simultaneously. That isn't a given. It could be the test for bias is going to heighten our concern about bias, but it doesn't heighten it in this case. It actually makes it more insensitive to bias. So let me summarize what I've been saying. Unmeasured biases are present in every observational study, but they may not be debilitating. They may not stop us from reaching fairly firm causal conclusions. Statistical theory can aid in avoiding mistakes that exaggerate the sensitivity to unmeasured biases. Large mistakes are possible in design and analysis. I think they're fairly common because I don't think most people are thinking about these issues when they design or analyze an observational study. Design sensitivity and Bahadur efficiency of a sensitivity analysis are two tools that guide design and analysis. They say if I got data from a particular probability model, which method would give me the least sensitive conclusions? If I got data from a different probability model, which method would give me the least sensitive conclusions? From that, I get some general principles, and I use those general principles to design actual observation studies. even evidence that bias treatment assignment is present may actually increase insensitivity to unmeasured biases. We have to analyze the data in these terms to figure out whether that's true or not. So let me close here, and I would be delighted to have your comments or questions.
Okay, let's take some questions from the live audience first, and the online audience can put down your questions in the chat box. We can go over there in a minute. Anyone from here? From the Newton Institute? Okay. I had a question for you, Paul, which is about the kind of, it's a usual question about your sensitivity model, which is kind of just the largest, the single block or pair that has the, and your model, the gamma kind of bounds the largest value. Have you thought about the ways of relaxing that a little bit, or does this kind of with this negative control outcome with the methyl mercury, does that alleviate that issue?
So it's certainly, the methylmercury data is certainly constraining what theta can be, and it's constraining it with actual data. So the data is telling us that some of the thetas are not actually plausible. Again, I think of the B gamma as taking what is in the data set a 1600 dimensional potential bias and reducing it to a single number, gamma. And that gamma is telling us how far from a randomization distribution we are without telling us its exact pattern. If you asked me for its exact pattern, I'd need some data like the methylmercury data to tell you that certain patterns are plausible and others are not. But it's not actually constraining what the treatment assignment probabilities would be. It's simply putting marks on a yardstick saying this particular theta is a certain distance away from randomization. This particular theta is further away. But every theta is ultimately someplace on this yardstick. This is the way I think about it.
Okay, thank you. Sean?
At the beginning, you emphasized how these four groups, how they differ from one another, like the pitch thickness and the curve thickness. I may have missed something, but you don't need those three, you don't need four groups, do you? You just need to match three controls to each case. Or have I missed something?
So there are two different issues going on. The formal analysis I did is the way you described. It's not distinguishing the three control groups. The argument for distinguishing the three control groups is that we'd like to vary some of the things we know are likely to be biases in an observational study among the control groups and see if they matter. If we see the control groups don't differ, as in fact we saw, right? We saw former binge drinkers very much like people who never had a drink of alcohol in their life. If we see that, we become less concerned, for example, about the fact that some people who don't drink because they used to be have alcohol problems and are now members of Alcoholics Anonymous, and they're fighting all kinds of issues, and other people just have no interest in drinking or have some other reason, perhaps a religious reason for not drinking. All those things are different among the people who are not drinking, and we're getting to see that maybe they don't matter very much. If you remember the, let me see if I can. These groups, which are really very different from one another, never drinkers, people who never drank in their life, and former binge drinkers, right? They're very different from one another in various ways, and yet they have similar HDL cholesterol levels. So their differences don't constitute an obvious source of bias in the comparison with the daily drinkers. That's the Campbell-Bitterman point. It's separate from the technical point I was making about having multiple controls. So you're right about the fact that the technical point didn't use the nature of the control groups.
Okay, a question from online from Richard Guo. Can you explain what is the rank range in the test statistic? If entries
Sure.
are ranked row by row, wouldn't the range within each row be the same?
So we're looking at the range of responses in each block and ranking those ranges from 1 to 406 and dividing by 406. So that's analogous to what you do with Wilcoxon's signed rank statistic. Wilcoxon's signed rank statistic will the absolute pair difference, but if you stop and think about it, if all you have is pairs, the absolute pair difference is the range, right? So we rank the ranges or ranking the absolute pair differences, and then we count up the ranks of the positive differences. That's just linearly related to Quade's statistic, which is using the ranks with the blocks for j equal 2.
Okay.
Does that help? Okay.
Yeah, Richard, if you still have questions, you can put it in the chat. Go to one. Yeah, Richard says thanks. One more question from online, Andrei Straka. How dependent are your results on the choice of design? Could any other block design change anything?
Yeah, so there are possibilities for doing better than I've shown you. So I have a paper in JRSSB in 2025 where I'm looking at the possibility of using essentially a subset of the blocks based on information contained in the blocks, no longer using the ranges, but actually throwing some of the blocks away as less informative. And that opens up a variety of possible tactics. A block has what is called a decisive pair. If the treated person in the block has the highest response or the lowest response in the block, and a control has the opposite. And it turns out if you focus on decisive pairs, you can further boost the design sensitivity. So that's opening up a different way of designing it. You can also use block designs with varying block sizes and so forth. There's a package, an R package, AA match, which constructs these designs, and you can use it to build a variety of different kinds of designs.
Okay. Sean, you have a follow-up question?
It's not a follow-up, it's a
Okay, separate question.
Are you assuming that the same confounding mechanism,
Could you speak up a little? I'm not hearing you.
are you assuming that the same confounding mechanism, the same confounders, are affecting the mercury and the HDL?
So I'm assuming that that the treatment assignment probabilities are assigning the treatments given the potential outcomes and the observed covariates. So it's all about this principal unobserved covariate, which creates the biases. The principal unobserved covariate is conditioning on the joint potential outcomes, including both HDL cholesterol and methylmercury.
Let's take one last question from online. So, Paul, you can read the question on the chat, but I'm just gonna read it for the record of the recording. Are there design and analysis choices in which the aim of satisfying as-if randomization, that is gamma equals to 1, and the aim of robustness to violations of as-if randomization, that is gamma greater than 1, do not agree? That is, can a design or analysis choice make gamma equal to 1 more plausible, but come at the expense of less robustness should gamma equal to 1 be false?
So that's an interesting question. I don't know of an example where that's true. I do know of an example where we are able to do both at once. So we did a study of whether general anesthesia accelerates dementia, Alzheimer's. If that were true, it would be problematic, and there's some lab science that suggests that you can give cells dementia, but nobody knows what it means to give cells dementia. It's the biological changes associated with dementia are produced by general anesthesia, ingredients in general anesthesia. So we did a study of people in Medicare. One of the problems in doing that is that people get anesthesia, get surgery, that's bias. They needed surgery, that's bias. They often have health problems that aren't fully cured by surgery, that's bias. So there's an enormous amount of bias when you compare people who get anesthesia to people who don't. They're wildly different. So we tried to reduce the size of the biases by looking only at people who had surgery for appendectomy, which kind of happens at random. So they're not especially interesting people who have appendectomy, appendicitis. And they don't have chronic problems, and generally the surgery is curative. They're cured after the surgery, and they go home, and this is the last thing they think about. So these were attempts to create a natural experiment, so we built that design. But again, we built it as a block design, just like this one. So it wasn't in conflict trying to create a block design with trying also to create a natural experiment. The natural experiment is there and the block design is there. It's a little bigger than this. I think it had 130,000 appendectomies from Medicare, and it had 5 controls for each appendectomy.
Okay, so let's conclude the session. Thank you, Paul, for a really interesting talk. It's inspirational. And thank you everyone online and in person here for engaging in this. We look forward to interact with you, Paul, if we can.
I'd love to, sure.
Emails or some other ways.
Absolutely.
Yeah. Thank you again.
Okay.